Okay, so for this part 3 of our 2D momentum videos, we're going to be moving slightly away from standard level 3 and moving more to some difficult things, so potentially some scholarship ideas here. So if you are just here for level 3, then probably stick to parts 1 and 2. That's pretty much all you need for level 3. We're going to be looking at this question here, which is if the impact time is 0.02 seconds, calculate the force experienced by the 4 kg mass. Now, if you're not familiar with what I mean by the 4 kg mass, you probably need to at least watch the previous video, which is part 2, where we go through this problem here. And so that will give you some background information on what's going on. But if you've already watched that, then sweet as. Now for this, you might already be thinking in your head, sweet, we know that the force is equal to the change in momentum over time, which will be correct. So we have our time, but we need to find our change in momentum, right? That's the thing we're trying to find. So we know that change in momentum is equal to the final minus the initial. And again, these are vectors, so we can't just simply add the values together because they're not scalars. Have to use vector triangles to find the final initial momentums. So that's what makes it slightly more difficult. So if we look back at part 2, this question, we have the final momentum of P4, which is coming down this way, which is obviously from here, that is the after scenario. And so we can draw that in. We can go, this is our P final, right? Because this is our P final, we're only dealing with the 4 kg mass, so that's our final momentum of the 4 kg mass. And minus the initial. So the initial is right here. It's this vector right here coming from that. And so we know that the initial momentum is like this. So that's Pi, right? But we're trying to minus Pi. So in order to negate the vector, we simply just flip it around. So that will be negative Pi right there. And so we can simply add negative Pi. And so this is the resultant vector. And so that is our change in momentum right there. This is the line that we're trying to find, the vector line that we're trying to find. And so although it may seem like it, we have no right angles, so we don't know any of these angles. We don't know the value of any of those angles. Even though it may look like a right angle triangle, it is not in fact, because we don't know the angle relationship between this vector and that vector there, because we don't have geometry. In the other cases, we do have a geometry, which was given by that right angle right there. And so we can apply that over there, but we don't have it in this case. So in order to solve this, we need to find the angle between the initial and the final momentums. So we need to find theta, right? So if I redraw these before and after vectors, so that's our before, and we can draw after right here. We have our P5 going down this way, and we have our P, so that's P5, our momentum of the 5 kg mass, and that's our momentum of the 4 kg mass, and then we had our momentum of COM, center of mass, like that. And then afterwards we have the momentum of the 5 kg mass like this, momentum of the 4 kg, and that again is our momentum of the center of mass. And so we know that this is a right angle, and in this case that is a right angle from our previous examples. We see that, and we see that right there. Okay, but if we define some more angles, we can define this as alpha, and we can call this angle here phi. Now we know that the momentum of the center of mass initially is equal to momentum center of mass finally. So this vector here is equal to that vector there. And so we can kind of deconstruct these before and afters, and we can redraw our this P4 over here. So that's that P4. Let's call this P4i. And we can take our center of mass, which is like that. So that's PCOM. And we see our P4 over there, and we can take this. So that's P4F, P4F. And so we can see that this angle here is phi, and this angle here is alpha. Now this looks awfully similar to the vector that we just drew. From these diagrams, we can see that theta is equal to alpha plus 5. If we know that, we can calculate alpha pretty easily because this is, again, a right angle triangle, and we can calculate phi pretty easily because it's a right angle triangle using our trig. Right? So calculating alpha, we can get P5 initially, which was, let's see, 10 kgs. So that was 10 kg meters per second, 10 kg meters per second, I mean, not just 10 kgs. And we can get our P4 initially, which was, I believe, 12 kgs meters per second. Yep. So that's 12 kg meters per second. And so that is opposite and adjacent, so that's our tan relationship. So alpha is equal to the inverse tan of 10 over 12, and our phi, P5 afterwards, was 5 kg meters per second. So that's the momentum of our P5 afterwards. And so the momentum of our center of mass was 15.62. And so phi is equal to, that's our opposite, we have our hypotenuse, so that's the inverse sine 5 over 15.62. And so that means theta is equal to tan 10 over 12 plus sine, inverse sine and inverse tan of 5 over 15.62. Right? And so putting that in the calculator, we get 58.47 degrees, or 1.02 radians, which is what I prefer to work in. Okay, so we know that this is 58.5 degrees, and so we can work this out. Now, again, because this is not a right angle triangle, we can't use our regular trig, we can't use our SOHCAHTOA. We have to use either sine or cos rule. In this case, I'll be using cos rule, which is a squared is equal to b squared plus c squared minus 2bc cos a. So theta will be our a, so that will be this value there. And so the opposite side, so delta p will be our lowercase a, and this will be our b, and this will be our c. Right? So we plugging this in, we get our delta p is equal to the square root of b squared, which we said was our p final, which was 14.8 right here. So for 14.8 squared plus our c, which we said was our initial momentum, which was 12 kgs meters per second, minus 12 squared, so plus 12 squared minus 2, 14.8, and then times cos, which we said was 48.47 or 1.2 radians. I'll be using 1.02 radians. And so our change of momentum is equal to 13.3 kg meters per second. There we go. And so again, using our equation that we saw in the beginning, force is equal to the change of momentum over time. We can plug in our change of momentum now. And that's all over the time we set in the question, which was 0.02. And we get 666 newtons. There we go. That is our final answer. So again, most of this difficulty comes from the fact that momentum isn't actually a scalar and it's a vector, and so when we add vectors, when we add or subtract vectors, we have to draw vector triangles to get the resultant vector. And so recognizing that the momentum of the center of mass initially is equal to the momentum of the center of mass finally. And so chucking this in, we can grab our two angles between the center of mass and the initial momentum and the center of mass and the final momentum. And we can chuck those two together to get our equation to find our theta. And then from there, it's pretty straightforward to find the force. So yeah, hopefully that helped. And again, this is more of a scholarship idea, probably won't come up in level 3. Don't quote me on that though. So if it does, Alicia, ready?